next speaker is Talu from Trend Micro on enabling dynamic analysis of legacy embedded systems in a fully emulated environment. His talk will be stressing the significance of emulation tools by showing how their emulation methods allow to transplant any given kernel mode binaries into a controlled environment. So without any further delay, Talu, I will let you begin your presentation, and thank you so much for joining us.
Okay, thanks. Thank you for the opportunity. So, hello everyone. Welcome to my talk. The talk apparently will be named Enabling Dynamic Analysis of Legacy Embedded Systems in Fully Emulated Environment. Let me introduce myself first. So I go by handle Eventify on elsewhere. I'm currently a researcher at TX1 Networks, which is a subsidiary of Trend Micro. I mainly focus on vulnerability research in my job, but I also have focus on other fields, including protocol analysis and hardware. So today we're going to talk about our little project, which we will go through it like this. We will talk about how we ended up with researching CE6, our goals and our background in this project, how the CE6 internal looks like, how its bootloader and part initialization goes, how its application loader looks like, and how the CE6 does memory management. And then we will talk about our proposal to do a kind of emulation on C binaries by using our method. And then we will conclude our talk with a demo. So our original goal in this research, we only wanted to study a particular device based on Windows CE6. And then we found out that despite CE6 is very old, but it is still being used by a variety of devices which might be sold or still deployed in the field. Also, as we mainly do vulnerability research, it is natural for us to study many devices, but it is actually quite impossible to buy every devices, as that will cost a lot of money, and space here is quite expensive in Taiwan. However, we ended up buying one of the devices actually for comparison to our project. Also, there are a couple of pros with emulation. You have fully access to hardware debugger 0 ports, which might not even be present on every hardware. Now, let's talk about the background of Windows CE6. Basically, Windows CE6, you can say that it is a horror from the ancient. Well, as it is a very old operating system still in use everywhere, but it hasn't been actively exported in the field yet. It runs everywhere, like in your car, maybe in any parking meters, in some aircraft entertainment systems, in subways, maybe trains, medical devices, or even power plants. And the main difference between NT and CE, well, Microsoft has a plan called Shared Source Initiative, which you only have to complete a checkbox while installing CE SDK. You check the checkbox and you will get some private source code. Windows CE is loosely based on NT kernel, but some of the behaviors are not quite the same. So you will see similar API names in Windows CE, and it will turn out to be not what exactly you will expect. And according to Microsoft, Windows CE is a real-time OS. So despite the differences we mentioned between Windows CE and Windows NT, it is possible to port some of our programs or attack methods originally used for NT-based systems until Windows CE. Let's take an example. So back in 2017, there's an attempt to port internal blue onto Windows CE, and the attempt actually worked on CE. And here's some current methods should you try to study in CE6 firmware. Before our research, there was a few limited options should you attempt to do research on any given CE6 images. There's a tool called emgfs, which have very deep roots back in the days of Windows Phone modding to extract the files from the image. But you cannot use them directly, as the tool will extract the file as is. We will try to explain the reason why behind this later on. For dynamic debugger, there is a wonderful project called CGCC, which ports a very old version of GCC onto Windows CE. It is possible to use the GDB included in that project to debug programs, even if the program was not compiled with GCC. In some of the devices, you can just simply plug in your USB drive and try to extract the files. However, the files you can extract using this way is very limited. You are unlikely to be able to extract drivers and libraries using this method. And even if you extract them, in most of the time, you cannot run them inside your environment with emulator from Microsoft or just with QEMU until we propose our method. So our research actually met with a very big failure during the start. So in the beginning, we studied how CE6 boots. We assume that it is just like ordinary x86 machines, goes to operating system after power on self-test is done. In CE6, there are two methods you can boot into the OS. One is what Microsoft called BIOS loader. It is much like U-boot in modern days. Another method is using any MS-DOS compatible DOS and use included tools from the SDK to load your operating system image, like what people did back in Windows 98 or 95 era. After the OS kernel loads, peripherals and devices will be initialized. Then it will go to loading programs. So, according to those points, we just assume C is like any other x86 OS, and it is trivial to emulate. So, CE6 firmware format, the CE6 image builder allows two kinds of output. One is called .bin, which has a tidy format, adheres to the struct pasted on the right side of the slide. Another one is NB0, is a one-by-one representation of the RAM, as some flash memories can employ execute in place, which means their storage area allows execution, and that saves time from copying entire OS into the RAM. Our target uses a .NB0 format, and contrary to common assumption, it is totally possible to convert it into a .bin file, and we can use load CPC tool to load the file. By pointing start address to the start of the flash with a context of NB0, we can pack it into a .bin. And then, with our naive approach, we are met with our first failure. This is roughly as far as we can go before we went with our another method. As the firmware requires some checks to special flash and I/O devices, this approach will naturally fail. However, we have done our attempt. We try to binary patch a great amount of part of this image and did make more progress into booting process. But then we decided to go against this route. Moreover, there are much differences between actual devices and QEMU. For example, our device uses an AMD Geo chipset. And in QEMU, we have either i440FX or Q35, and they are quite much different. We also thought about creating corresponding chipset and devices in QEMU, but that will take a great amount of resources to do so, and it will require a very deep understanding of the target platform. As we mentioned before, we even tried to binary patch an entire graphics driver into the image. However, that took too much effort, and we did not succeed by the end. So from our first failed attempt, we learned that assuming we can accumulate in any image is a very naive approach, and we were met with failure most of the time. So we came to the conclusion that accumulating an image as is could be proven difficult. Should you go with binary patching path, you will need to have some deep knowledge about the target platform. And at this point, the amount of binary patching we have done to the image had made us very, very uncomfortable. So we cannot quite tell the difference between we are working hard or it is hardly working. Then we have a round 2. Apparently the method worked, but not in a way we was aiming for. What we have learned from our round 1 is that we cannot go straight from firmware to accumulating. However, as we go deeper into this research, we thought about if it's possible to port binaries from another image to our own image. Like we just port all the drivers and libraries and bundle them with our own image. Before this research, the method actually worked for another device based on CE6. But for this device, it employed architectures in CE correctly, and the binaries are integrated deeply with the image, so the method did not outright work. Precisely said, the vendor actually invokes system and kernel flags on the files. So in order to achieve our method, we need to figure out that if we can extract drivers and files from a CE image, bundle them into our own image, and make the files actually run in our own image. Fortunately, for extraction, we can use eImageFS. For building our own image, we have CE6 SDK, which is based on Microsoft Studio, and it is available to us. However, as we try to build our own image with those extracted files, the build actually succeeds, but CE crashed right away as we booted it up. So we were very confused. We wonder why it crashed so hard, and it crashed on a very early stage of booting process. Then we take a deeper look into source code of CE kernel and its application loader. At this point, we were thinking about if CE should look like an anti-kernel. It turns out not. The application loader in CE6 is like what it is on NT, will parse P header, loading libraries, allocate a size of memory, and jump to the binary's start address. However, there is a major difference in CE that makes our image approach crash. In NT, if a PE has its image space fixed, and the address it asks for has been occupied, the kernel should check if the PE does have a relocation directory. And if it doesn't exist, it should not load the PE and should go to fail. If a directory exists, then the kernel will assign a free address, then do relocation. In Windows CE, the behavior is very bizarre. If a PE does not have relocation directory, it will still load the binary in a free address and run it. This will outright crash the system in most cases, as it could imply tons of segmentation violation. So we have a wonderful graphical representation of what will happen should we outright move a fixed address binary from a CE image to another. In most cases, our custom image will not have the same address as our target, and will likely have tools for debugging purposes. If we just move binary from one image to another, most likely an address conflict will occur. And everything will explode. Yes, most of the time it will outright crash the system. If it just works in your case, there are two possibilities. Either the binary does not have its address fixed and it does have a relocation directory, or you are having a very good luck of not having an address conflict. And let's take a quick look about CE6 Memory Management. In CE6, unlike CE5, it does not use a concept of slots. In CE6, any process has a 1 GB of virtual memories. Also, the flashes are usually executed in place to save loading times. That would imply most drivers and frequently used PE will have fixed addresses in the memory and also in the image. And we should talk about how CE6 image is bundled. In CE6, when an image is built with Visual Studio, any unessential segments from the binary is stripped just before it's bundled into the image. As the image builder already figured out a proper address layout, and a relocation directory is no longer needed at that point. However, in a step before bundling, linking happens, and we need a relocation directory to link it against other libraries. So, to achieve what we want to do, we came to some conclusions. We must reconstruct the relocation directory as it is required for us to bundle the image into our custom image. We then came up with how to actually implement our approach. We call this static reconstruction of relocation information in PE. This kind of approach actually has a prior art, which the link is below, but it's for dynamic analysis only. Apparently, we cannot run the binaries at this point, so our approach must be done by static analysis only. In our approach, we actually know start and end address of each PE by looking into their headers. We theorize by scanning through entire binary, and we look for references to the address into the range between start and end. We can collect all of the addresses that needs to be relocated. However, for code and non-code segments, they must be handled differently as their layout isn't quite the same. For code segments, we will try to locate all function epilouge and prolouge, then iterate through every function. Then we check for every instruction. Should the operand makes reference to the range between start and the end address, we will place that address into relocation directory. For non-code segments, it will be quite simple. These kind of segments will contain things like vtable and string tables. And in the case of both Microsoft Visual Studio compiler and Boolean compilers, they are both conveniently aligned. So we can just scan through the segments with a 4-byte interval and check if any bytes matches the range. This could be a very poor approach, but it actually worked quite well. And after our couple approaches, we figure out that something is still not right because we're still having crashes while booting up the binaries. So we take a quick compare against normal binaries and figure out that we're still missing a ton of entries. So the devil is in import address table. It is possible to reference an import by a name or by ordinal. If it's referencing an import by the name, then it will store a pointer to character array, and that address must be put into the relocation directory. After we have harvested most, if not all, of the address, we can now finally rebuild the location directory according to this struct and write it back into the binary. So here we will go to our demo. We will call this rerun your device without your hardware. So let me try to locate the window. Hello, and welcome to our demo for reconstructing relocation information in PE. Here we have a list of files extracted from the firmware we are emulating. The files has been preprocessed to remove unnecessary segments, and being extracted from a CE image, they naturally don't have a relocation directory. Here we can prove this from the CFF Explorer. The relocation directory is required for us to put these files back into Visual Studio and bundle it with our own image. Here we will run a script, which basically iterates through the files, running ida-python script with our own search algorithm against the files to determine the addresses need to put into relocation directory. As the process goes, the list of addresses need to put into relocation will be generated. This process is very slow, so we'll fast forward to recreating the relocation directory in the binaries with this list of addresses. Now we are going to recreate relocation directory and write them into the files using PE file. Apparently some of the writing will fail as this is a very early version of the POC, but it still allows us to run some of the files from firmware. Some of the files will still have relocation information attached as they are not compiled with specific flags, hence their relocation is not stripped in the original image. Once the writing is done, we will rebuild the image with Visual Studio and run the image afterwards. In Visual Studio, we attach our auto files into the manifest, so the image builder will include the files which our target is required to use. Later in our research, we figured out that we don't have to attach all of the reconstructed files to achieve our target. Let's start building. The building process is very slow, so we'll fast forward to emulation. Now we will try to run the target in our homebrew image using QEMU. As the target requires some auxiliary files such as resources, we will copy them from elsewhere to its destination. Now we have a working start as you can see, we are
ready to
succeed
rumble.
in emulating a binary from our target device. However, in this case, we haven't. There are some restrictions on the target device's binary that we haven't got through it yet. So the binary actually checks for some kind of license files, and we still haven't binary patched files. And in the case if the demo video doesn't go quite smooth through Zoom calls, I will just paste the demo video onto YouTube after the talk finished. And here will be a much clearer image to show everyone that we can actually do a firmware simulation in QEMU. So with our method, you can totally run bundled CE6 binaries without hardware. By using this method, you will have access to tons of debug tools, such as KTL. You will have 0 outputs, which is very quite useful. And you can use WinDBG. In our method, it is around 98% accuracy, which is good enough to run most of the binaries. We know it's 98% because we compared it with original binary, then strip the binary of relocation directory and reconstruct those binaries relocation directory and compare the counts inside relocate. We plan to open source the tools we used later on. Because the code is written in a POC style, it is essentially a pile of spaghetti right now. Hence, we will publish it after we clean it up while making our accuracy higher. And we will come to some suggestions for vendors and remarks. For this particular vendor, a proprietary format is used to pack firmware. It is quite difficult to dissect. However, we did prevail, and we did wrote a dissector to extract the files and CE image. So anything bundled within firmware will be extracted and being looked at. And we have proven many times, any proprietary format does not prevent anyone from breaking into your system. And we encourage vendors to have a friendly community and research outreach. We think this approach is very noble. And for our future work in this project, yes, we will try to combine this research with any fuzzer should the fuzzer runs on CE, or we have figured out a way to not port it to CE but still make it work. For simple programs, there's a project called WCE Compat, which is like using Wine on Linux to run Windows programs. It is a Windows CE compatibility layer. And during our research, we have came across a book which helps us very much. So we have to say a very big thanks to Pavlov and Belevsky. And also a thanks to Microsoft for shared source initiative, although we might prefer open source. But for this project, it will be next to impossible to achieve our research without it. So that will conclude most of my talk. And for questions, you can actually send them to my work email, and I will try my best to reply to the questions.
Friends, if you have any questions, please send them across via the Zoom chat.
So are the questions in the chat right now?
No, I don't see any questions right now in the Zoom chat.
Yeah, I was worried about if my demo video did have audio inside your Zoom call.
Yeah, it did, at least for me. I do not know about the rest.
Nice.
If you would like to play it again, you can. There's an option in the when you share your screen to enable audio video optimization. If you would like to play it again,
I would just paste the video onto YouTube after the talk is over.
That's also fine with us. Okay, friends, any questions? Time is kicking. Otherwise, we could open for the coffee break now. All right, Talu, there are no questions as of now, but friends, this talk will be recorded and is going to be uploaded on our YouTube channel. So you could also refer to it later. The video of the demo will be also posted on the YouTube channel, so you all can view it. And if you have any questions, Talu has mentioned his email address as well, so you can talk to him and contact him directly as well. Thank you so much, Talu, for sharing your experience and learning with us at hardwear.io USA 2021 edition.
All right, thank you, everyone.